Okay, now we're going to look at a topic, a subtopic of this Apollo hoax that few investigators, if any, have looked at carefully. And that is the surface of the moon as depicted in the Apollo photographs compared to how we know it is and has to be. And we're going to start first on Earth with meteor showers. These are periodic bombardments of the Earth by small particles. And they occur, this phenomenon occurs when the Earth in its orbit around the Sun plows through the old orbits of comets, mostly comets, a couple of asteroids as well. And in these old comet orbits, and when I say old, I don't mean the comet itself is old, but the debris from the comet has been sitting here for as long as the comet has been going around, okay? So the Earth plows through these comet trails where there's all this debris, and it's not just dust. I like this depiction because it gives you an idea of the number of particles, which is a vast number, but it's not dust at all, at least not mostly. The particles can be are pebble sized mostly, and they get up to the size of baseballs, softballs, and that kind of size. They're not usually very large, but they can be sizable. Now, there are about a dozen regular periodic meteor showers, yearly meteor showers that is. And in tables like these, we are told the length of the shower and most critically the number of particles that we can expect to see hitting the Earth's atmosphere. And this is the zenithal hourly rate. And this is one such. And so as the Earth goes through the path of the comet, the number of particles increases, that we hit increases to a peak. All right, but that peak is what's shown here. These tables show the peak, but of course we're not always at that peak. So to get an idea of the number of meteorites that we're encountering, we're going to take half of that peak, and we're going to take half of this duration of the shower to get an estimate of the number of particles that we're talking about. But before I do that calculation, I want to make this important note. The meteor counts given here are used because they are readily available, not because they are definitive. In fact, they are undoubtedly a vast underestimate of all the meteorites that strike the Earth and the Moon. In the case of meteor showers, this is because the zenithal hourly rate represents only the number of meteors a given observer can be expected to see from any one location on Earth, not a literal count of all the individual meteorites striking the entire planet at any given time, which of course would be an incomparably larger figure. In the case of bolides, which I'll describe in a minute, it cannot by any means be assumed that the instruments used to record the bolide strikes actually succeeded in detecting all the strikes in the given period. They most probably did not. Okay, so here we go with this calculation. As I said, we're going to take half the days. We're going to use that table that we just saw, and we're going to take half the days and half of the ZHR, and we just multiply, simple arithmetic, and we get this total for the year. Okay, about 67,000 meteorites from the meteor showers. But that doesn't include the sporadic or background meteorites, okay, which occur regardless of the showers. There's a constant bombardment, independent of the showers, which is roughly 5 meteorites per hour. So you multiply that by 24 hours, 365 days a year, and you get this figure. So the total altogether comes out to 111,000 and plus, okay, meteorite strikes from meteor showers per year. Now, the life of the moon is over 4 billion years, and I'll explain that a little better in a second. But what we're looking at, what we're seeking to find is the number of meteorite strikes that the moon has suffered. Now, the moon and the Earth obviously orbit the sun together, so we can get a good idea of that number from the meteor strikes that we observe on Earth. Okay, going now to the moon. As we said, 445 quadrillion strikes over 4 billion years. Okay, and the surface area of the moon is 38 quadrillion square meters. So you divide that number by that number and you get 12 meteorite strikes per square meter of the moon's surface. Now, as I said earlier, most of the meteorites are the size of large grains of sand to pebbles, but some of them are about the size of a baseball or a softball or even larger. A softball-sized meteorite would be about 4 inches wide, and when those objects strike, when any object strikes the moon, it leaves a crater about 10 times the size of the object itself, diameter-wise. So a 4-inch diameter meteorite, which would leave a crater about 40 inches in diameter, which would cover the entire square meter that we're talking about here. Okay, so these figures already tell us that the moon is completely covered by craters, at least small craters. This is a post-production editorial note. I made a couple of mistakes in my calculations in the original video. So now this number is different, this number is different, this one, and this number is slightly larger. The yearly total for the meteorites from the meteor showers. More significantly, and also this number is different, but as I was saying, more significantly, I skipped trillions and went straight to quadrillions for some strange reason, which I could explain, but you don't want to hear my excuses. So this is 474 trillion. It's not quadrillion. And here we have trillions and trillions, not quadrillions. Okay, but luckily for me, since I made the same mistake in both places here, the division is turns out to be roughly the same, or the figure from the division turns out to be roughly the same, 12 meteorite strikes per square meter. I might as well take this opportunity to make something else more clear than I did before, and that is that the moon, being smaller than the Earth, obviously gets hit by fewer meteorites because it presents a smaller surface to the oncoming shower that hits both the Earth and the moon. Now, these figures are all based on the Earth, which again is much larger. So they aren't strictly accurate for the moon. However, as I did explain, all of these figures are vast underestimates even for the Earth. So that would tend to compensate for the fact that the moon is smaller and gets hit by fewer meteorites. In any case, all of these calculations and all these figures are just aimed at getting a broad idea, a ballpark figure for how many meteorite strikes we can expect the moon to receive. There's no pretense of exactitude here. Now, so far we've been talking about meteor showers, and that's not even half the story, because there are bolides, which are large objects. They're in fact small asteroids. And now we're talking about meters in size, okay, up to many meters in size. This is the largest bolide strike of the Earth in the past 100 years. It's the Chelyabinsk meteor over Russia. And this is such a cool video that I'm going to show it to you. And now this meteorite came in and it was detected through numerous, what do you call them, dash cams in this case, and other photographic records. And here it comes. And there it goes. Now I'll run through it again a little slower because it's so cool. It takes a while to get over this point, and then it explodes right there. Okay, and then the remaining fragments continue. That's the main one, and then there are trailing ones, and the trailing ones are burning, and the main one keeps on going. As I said, there were a number of recordings of this strike, which is one of the greatest, phenomena, astronomical phenomena we've seen. This occurred in 2015. Now, there was hardly any damage to the Earth's surface from this meteorite, which was about 20 meters in diameter. It broke up. As we saw, it exploded. And a number of chunks hit the Earth, but this was the largest right here. It just hit a lake and went down to the bottom, and they recovered a couple of the largest pieces. This was the largest piece here. I think that weighs about over 1,000 pounds, something like that. But the important point for our purposes is that this bolide didn't even damage the Earth significantly. It caused a lot of explosions, that windows bursting and that kind of thing. And so it did injure a number of people, but it didn't leave a lasting crater or anything like that. So this is a very significant point. The fate of A, meteors, and B, craters on Earth. Because of our thick atmosphere, most meteors are destroyed or at least drastically slowed down. Therefore, few craters result. Surface alteration, that is erosion and geological activity. Because of this, on Earth, craters are erased relatively quickly. We're talking about plate tectonics, volcanism, erosion from wind and rain, water, all that kind of thing. Okay. Now, the fate of A, meteors, and B, craters on the moon. Because the moon has no atmosphere, all meteorites hit at full speed and with full force, and all meteorites produce craters. There's no weather or geological activity on the moon, therefore there's no significant erosion. Craters remain forever. These are the bolides that hit Earth during this period, a 20-year period, as recorded by U.S. military installations of some kind. The articles didn't explain. But anyway, the number is what's significant here. And these are bolides in the 1 to 20 meter diameter range. Okay, 556 over that 20-year period. So you multiply these two figures and you get about 110 billion meteorite strikes, bolide strikes that is, in 4 billion years. And you divide that figure by the by the surface area of the moon, which we saw earlier. Okay, and you get 2,900 strikes per square kilometer. Now, let's take the average impactor, the average bolide, as 4 meters in diameter. As I said, by definition, the bolides that we're dealing with are 1 to 20 meters in diameter. And of course, they can be larger than that. But anyway, conservatively, we take a 4 meter impactor as the average. That gives us a 40 meter crater. And that's this area right here. And you multiply that by 2,900. And you get a surface area of 3,600,000 square meters. Okay, but we're talking about the number of strikes per square meter, per square kilometer. All right, so we get this figure, and a square for the size of the craters collectively on the surface of the moon. And that's over each square kilometer, which is only 1 million square meters. So 3,600,000 divided by 1 million is 3.6 square kilometers of crater area per square kilometer of moon surface. In other words, the moon is covered many times over by craters, by not only the meteor shower craters that we saw earlier, which would be mostly small craters, but these larger craters as well. The moon is literally covered by craters. Many times over, as a matter of fact. And scientists know this, astronomers know this with regard to the highlands, okay? where you see in photographs all these craters. Now, what I'm going to argue is that the Maria are also, the lowlands are also covered by innumerable craters. Okay, so to think that the Maria are smooth and craterless is actually a misconception. We get the best idea of how blasted the moon is by craters when we look at the far side of the moon, the side that's always facing away from the Earth. It is totally covered in craters, craters everywhere, and craters on top of craters. Okay, that shows you how blasted the moon is by meteorites. Now, the only reason that there are Maria without all those large craters is that after 500 million years of the life of the moon, also the life of the solar system, during that first 500 million years, there was this bombardment of the moon and all the solar system bodies by large impactors, by planetesimals, okay, small asteroids, planetesimals. And that went on for about 500 million years. And then all of those bodies flying around collected, they aggregated into the planets and moons that we know today. All right, so that bombardment ended after 500 million years. But toward the end of it, those large planetesimals pierced the moon's near side, and that's because the moon's near side has a thinner crust than the far side. They didn't pierce the far side crust for reasons that I don't want to explain. The near side of the moon has a thinner crust. Okay, so lava, molten lava, rose out of the interior and covered these areas here, which is the Maria. All right. However, ever since then, and this is where the 4 billion years comes in, the moon has been bombarded by meteorites, as we saw, both meteor shower meteorites and bolides as well, just like the Earth, except that all the craters remain on the moon. So it's a misconception to think that the Maria regions are more or less free of craters. First of all, we can see that there are a number of craters in them, but we'll see more. Okay, and the moon has been bombarded ever since then, as we see in recent photographic and video records. This is a 1953 photograph of a meteorite strike. It was estimated that the impactor was 20 meters in diameter, and it left what is estimated to be a 200 meter wide crater that was found. This is a video from 2013, I believe, that shows a meteorite strike. I'll show that again. That's a meteorite strike, caught on video. Here's another video, and for some strange reason, this institution had to paste these large logos all over the moon, but this is the moon, okay, and this is where the strike is going to be, and there it is. Okay, so this is also 2013. These two were from 2013. So the bombardment of the moon has gone on unimpeded ever since that late heavy bombardment, and that includes, of course, the Maria as well. So before we look at the Maria more specifically, let's look at some of these famous craters on the moon. This is the most famous of all, Tycho. It has this this what do you call ejecta blanket. Okay, it's called an ejecta blanket. This material that was blasted out of Tycho when that meteorite strike. It also has crater rays. These things here, okay, which go as far as here as we can as far as we can tell. Okay, literally hundreds and thousands of miles across the surface of the moon. And this is what one astronomer said about Tycho. As you gaze at the ray system try to appreciate the force behind an impact that would scatter boulders more than 1,000 miles across the surface of the moon. It is popularly assumed that these rays have the texture of face powder and that an astronaut would have difficulty detecting them if he were standing in the middle. Such is not the case. The brighter rays are made up of ejected rubble that consists of crushed rock and boulders that are up to a couple of feet in diameter. Large rays are commonly several feet thick and would be difficult to walk through. Now this here, where he says that the boulders are up to a couple of feet in diameter, that's a vast understatement. And I'll explain that in just a little bit. But first I want to point out that this is Tycho here, all right? Now this is a composite image. It's not one photograph. We would never see the moon exactly like this. And I don't want to take time to explain why, but the point here is that Tycho is only one of many craters, innumerable craters, large craters. And all of these craters would have left ejecta blankets and crater rays and a whole lot of material all over, around where they hit. The only reason that Tycho, the crater rays and ejecta blanket are so conspicuous is that Tycho is younger than these others. Okay, so as you see here, Tycho's crater rays and ejecta blanket are conspicuous. Most others are not so conspicuous. Tycho crater is one of the youngest large craters on the moon, and it is for this reason alone that its ejecta blanket and crater rays are still prominent. Over time, these features fade in color and brightness due to both solar radiation and micrometeorite bombardment. All of the countless large meteorite impacts on the moon have spewed prodigious amounts of material in the form of boulders and rocks over large areas of the moon's surface, and this jumble of material remains there forever. Here are another three well-known craters on the moon. This is the most famous of these three, Copernicus, this is Kepler, this is Aristarchus. Okay, and these are these craters right here. And you see that their ejecta blankets and crater rays cover a large portion of this west side of the moon. All right, and this is all west side of the Maria. I'm sorry, western Maria region. Okay, and here they are again. So look at that large ejecta blanket of Copernicus, and this is a little closer. And notice this what do you call it, string of craters. Those are not independent craters. Those are craters created by the objects blasted out of Copernicus when the meteorite created Copernicus. So imagine huge chunks, and we're talking, God knows how large these objects were, flying out of Copernicus, going up into space, and coming back down, and creating these craters here, the largest of which are 4 miles wide. This one right here and this one right here. Okay, and then the smaller ones are about 2 miles wide. That's what these are right here, these craters here. Those are not mostly, for the most part, are not independent craters. They're secondary craters from the blast that created Copernicus. That just shows you how much material and the size of the objects that we're talking about that are blasted out of craters, out of large craters. For comparison, this is Meteor Crater in Arizona, also called Barringer Crater, and it's the largest well-preserved crater on Earth, but it's only 3/4 of a mile wide. Okay, going back to Copernicus, this is a closer view with higher resolution, and these craters here, okay, which would be a little closer to Copernicus here, but they're not well resolved, if at all. Okay, those craters are on average about 1.5 miles wide. These innumerable craters, all right, you can even count them. 1.5 miles wide. That's still twice as wide as Meteor Crater, as Meteor Crater. So that just shows you how much material is blasted out of a crater like Copernicus, which is not an extraordinarily large crater by moon standards. This is a small crater. This is Censorinus. It's only about 4 kilometers wide. and look at the boulders on the edge of this crater. Okay, you would think that it was smooth. There was nothing around it in this large-scale photograph. But if you look at it more closely, these larger boulders are about 150 meters wide. That's twice as wide as a tractor-trailer, or about the size of a very large apartment building, taking up a good amount of a city block. So those are huge objects from just a relatively small impact, making a relatively small crater. And of course, there are a whole lot more boulders, house-sized and car-sized. Okay. Now let's get back to the Maria. They look fairly smooth, all right. But you can see that there are already here. You can see that there are craters in the Maria. So the Maria are not crater-free by any means. Okay. You can see quite a number of craters already. But some areas look smooth, like take this here. This is Sinus Iridum, all right? It looks smooth, right? When we look more carefully with a higher resolution photograph, or in a higher resolution photograph, we see a number of craters, all right? This one right here is Laplace A, and it's 8 kilometers wide. So these two here are about 4 kilometers wide. But the closer you look, the more craters you see. Now we're going to look more closely even at this area right here, from there to here. Okay, this is a close-up from a more recent lunar orbiter, and what you see is really quite astounding. Innumerable craters. Not only the well-made out ones, the well-resolved ones, but the ones at the near the limit of resolution. You can see that there are literally countless craters, small craters. In this view here, these two parts of this photograph, the well-made-out craters, the smallest of the well-made-out craters, maybe this one here or this one here, these are about 400 meters wide. Okay, but again, look at how many small, barely resolved craters there are, just at the limit of resolution, or just below, as a matter of fact. Okay, they're innumerable. Yep. And here, this is an enlargement of this region right here. You can see very clearly all these craters coming into view, some of them barely. So the moon, including the Maria, are in fact covered by craters. This is shown here in this region as well. This crater right here is 6 kilometers wide, but we're going to focus on this square right here, this piece right here. Now this looks fairly smooth with just a couple of craters there. This is what it looks like in a closer view. These 3 craters right here are about 300 yards wide. Okay, and this crater right here is 100 yards wide. But there are, countless other craters in a jumble. Okay, all kinds of craters, small and large. And this is there's no reason to think that this part of this Maria is atypical. All right, this undoubtedly is what all the Maria on the moon are like, literally covered with craters. And if we could zoom in even closer and get an even closer resolution, even better resolution, we would see even more small craters. Now, the Apollo landings were in various terrain, okay, in varied terrain. There were 6 of them, and the Apollo 11 and 12 were in Maria, 14 and 16 were in highlands, and 15 and 17 were in at the edges of Maria, but surrounded by mountains, in mountain ranges. Okay, and yet, despite this variety, and despite what I showed you about the moon being having to be covered in craters and boulders, these are the typical photographs that we see from the Apollo missions. This is Apollo 11. Where are the craters and boulders? Apollo 12. Apollo 14. This is in the highlands, where you would definitely expect to see craters and boulders. Apollo 15. Apollo 16, mega highlands. We're going to look at this a little later. Apollo 17, fake mountains, okay, phony, washed out mountains, but right now we're focusing on the surface. In none of these photographs, and I could show you literally hundreds, if not thousands of photographs just like these, this is the general view that we get from Apollo of a featureless landscape, a lunar landscape without any significant craters or boulders at all. Literally just handfuls of decent sized craters and boulders. It is totally unreal.